Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Quadry Chance with us today. Hey, Quadry.
Hi, Frank. Thanks for inviting me on. That's really cool.
Well, thank you so much for getting to talk about your very awesome article. And Quadry, where are you located at?
Right now I'm in Gainesville, Florida. I'm a grad student at the University of Florida.
Very cool.
So,
How far along are you?
I'm finishing my 4th year now, so graduating soon-ish.
Dr. Chance, Dr. Chance. I look forward to saying Dr. Chance. That'll be very awesome. Very cool. Congratulations. Almost there. Almost there. Let's see. It is Memorial Day, May 29th, as we record this, in Florida. So Florida is probably in full swing in its summer.
Oh yeah. It's actually kind of cool this weekend. We got a weird kind of cold snap, so it's only 80 degrees outside.
Wow, wow. But it's
So
probably still 80% humidity or something. So
yeah, but I got the smoker going for some barbecue for later for some friends. So
oh, I'm coming over. I'm gonna please
take a quick
please
flight.
save a rib or something for me. That'd be great. Very cool.
I actually saw that you were at ASU.
Yeah, I'm in Arizona State.
I'm a Wildcat. I went to Arizona for my undergrad.
Well, very cool. Okay, so you know all about the dry heat here.
Yeah.
Yeah, so the power switch hasn't quite been hit yet. We're still sort of floating in the 90s. We haven't hit the the 110, 115 kind of stuff.
Yeah.
But it's coming.
Yeah, I take that over this.
Very cool. Well, maybe you'll come back as a Wildcat for your postdoc or something. I don't know.
Mm.
Dr. Chance. Very nice. And Quadry, what do you like to do for research?
Exoplanets, specifically more like demographic questions.
Okay.
So I really like trying to figure out, why don't we have certain kinds of planets in our own solar system? Like, how did these planets form? How's that different than our own solar system? So I really like to do all sorts of questions in like sort of that area.
Very cool. Of course, that's a very hot topic these days.
Mm.
So that is going to bring us to this very awesome APGA article. We are in the open access era, people. So this one is open access, as is all our content now. So you can go grab a copy for free. Go get one. Signatures of impact-driven atmospheric loss in large ensembles of exoplanets. And Quadry, take us away.
All right. I guess first I'd like to thank my co-authors, my PhD advisor, Sarah Ballard, and my bridge program advisor, Kayvon Stason.
Very cool.
This took a couple of years to come together across 2 programs, so shout out to them for making it happen.
Yes.
So I guess this paper was kind of born out of, we finally have enough planets, the standard, we have over 5,000 exoplanets that have been discovered.
Yep.
We finally have enough planets to really look at the characteristics of them and have enough statistical power to say things about them. And so this was really about the atmospheric evolution of planets. So people watching this have probably heard of the radius gap, where there seems to be a dearth of planets around like 1.8 Earth radii, where on one side you have rocky planets, on the other side you have gas planets. And the way that is produced, I think there have been like several waves of different, this is the way this happens, or this is the way it happens. But
yeah,
broadly, you have photoevaporation, core powered mass loss, maybe something from giant impacts, and you can produce this radius gap with all of them. But they all have specific signatures, like to individual planets, that should tell you which one is dominant at least. And so this paper, we decided to take like a little toy problem of, if we have a population of planets that we photoevaporate and we do giant impact atmosphere loss on the same population of planets, is there anything that we can see that would tell us what happened?
Okay, I'm with you. Cool.
So basically we took some in-body simulations from a previous paper, which we knew already reproduced the Kepler planet statistics.
Oh, nice.
And building off of work by beer sticker and shipping on the splashing of the atmosphere off of an
Ooh,
exoplanet after a giant impact.
okay.
Combining those two things, we basically popped out two populations of planets and did a little fake Kepler survey on them.
Right, right.
And we did end up with a couple of neat things that maybe could point us in the right direction as far as what is the actual dominant atmospheric loss force in nature.
I'm with you. Very cool. Good. Okay. It's an intro, and let's talk a little bit about those in-body simulations.
So it's kind of strange actually. So when I started this was during my bridge program, for which I was going to be there for a year or two at the Fisk Vanderbilt Bridge program. And so I didn't really have time to run an entire suite of planet formation and body simulations, like from 0 to 10 million years,
Oh yeah.
in the sort of allotted project time. So,
Yes.
so where I could like get that done, write my master's thesis, and then graduate, and then go to a PhD program. So, Sarah has previously collaborated with Rebecca Dawson,
Okay.
and Rebecca Dawson and her co-authors wrote a paper in 2016, trying to figure out if there is like how the Kepler dichotomy happened. Now, I think this has sort of fallen out of favor, but there seems to be a group of planetary systems that are very close, compact, flat, dynamically cold,
Yes.
and ones that are not as compact or flat, so dynamically hot.
Yep.
And there's a lot of effort going toward trying to explain how this comes to be. And this paper was part of that effort. So they had a bunch of planet formation simulations with different disk properties, and they tried to reproduce the Kepler planet statistics, which they did. So we ended up using their simulations in order to not have to spend months running a new set of simulations.
Get the maximum leverage out of those simulations you can. Yes.
Yeah, kill as little trees as possible.
There you go. There you go. Very good. Okay.
So using those simulations, we basically stacked on top of that in a sort of post-processing, or maybe not post-processing, just like injecting processing steps using the atmosphere escape modules from vPlanet.
Okay. Okay.
vPlanet is a suite of different software, different simulation things for basically every piece of a planetary system's evolution. And so we use that to simulate photoevaporation, and we did our own kind of toy modeling of the giant impacts problem.
Okay.
Because the dynamics of that are really complicated. When you have a
Indeed.
large impactor impacting a planet with a gaseous atmosphere. But in essence,
Yes.
if the impactor is large enough, you will remove 50 to 100% of a primordial atmosphere from a protoplanet.
Yes.
And that's kind of the key thing that we used. It became more tractable when we can just assume that if this planet has experienced an impact, it has lost the vast majority of its atmosphere.
Okay. Okay. I'm with you.
So go ahead.
I was just going to ask one question on the in-body simulation. So did you actually get the like the dump files? So you tracked the time evolution of all the particles in that in-body?
Yes.
Okay. Okay. So
we tracked.
I got it. I'm with you. Yeah.
We tracked each impact. And so I guess we could go.
Quite a chunk of data.
Yes, it was also quite a chunk of time.
Yes. Very good. Okay. Good. I'm with you. Okay.
So since we have these simulations which reproduce the Kepler statistics, we can sort of have some confidence in that the statistics that we see when we run our own fake Kepler mission will result in the same thing. Cool. And so start out with a set of 80 systems that are from the dynamically cold population and 80
Okay.
systems that are from the dynamically hot
Okay.
population,
Okay.
and then put those through both photoevaporation and giant impact atmosphere loss.
Okay. All right. And so just for notation as we go through here, ED10-2 is going to be the cold.
Yes.
And ED10 to the fourth is going to be the hot. Okay.
Mhm.
I'm with you. I'm good. Okay. Okay. Signing radii. Ooh, that's a good one.
So yeah, that's part of the process I just described. So we assume that the accretion of their hydrogen-dominated atmospheres stops at about 5% for these planets. That's too much for some of them, too little for other ones, but on average, it's about 5%.
Okay.
Now, this does increase their planet radii, which will increase the transit yields when you run our simulation. So we did have to account for that.
Yes. Mm-hmm.
So in order to like isolate, you know, what the results of each process are, we ran them in isolation, even though that probably doesn't happen in nature.
Okay.
You can generally like everything will have to go through photoevaporation, just like everything will go through a stage of giant impacts. So,
Mhm.
um, and I think for we basically determine that if a planet lost more than I think 90% of its atmosphere, that counts as lost atmosphere.
Okay.
And if it had more than 10% of the remaining atmosphere, that counts as kept atmosphere. Um, this enables us to do simpler statistics, and since we're already sort of doing a toy problem, I
Yeah.
think that's a reasonable assumption to make.
I agree.
So rocky planets basically get their own mass radius relationship, and ones with atmospheres get a different one.
Mm-hmm. Mm-hmm. Okay.
Um, and you can see here,
Separate it. Yeah. Okay.
you can see here in the giant impacts loss. This is a very simple sort of, did you put enough energy into the planet to liberate the gas into infinity?
Okay.
Um, and we found that basically the mass of all of the impactors exceeds the cutoff mass for that happening. So if a planet suffers a giant impact, then it will lose its atmosphere, at least under this description.
Yes. Okay. With you. Mm-hmm.
And so if we also make another assumption that if
Yeah.
a giant impact occurs before the gas disk is dissipated,
Oh.
the planet will be able to reaccrete its atmosphere because the accretion timescale is so much faster than the timescale between impacts.
Okay. With you.
But once the gas disk is dissipated at a million years into the simulation, once you have an impact and you lose your atmosphere, that's it.
Okay. Okay. All righty. Good. I'm with you. Yeah, let's take a look at figure one. Histograms.
So yeah, this is showing the number of giant impacts during the planet assembly process for each planet. So this is the distribution of all planets. In purple is the ED 10 to the 2. So that's our flat dynamically cold systems, our multi-transiting systems. And green are the sort of likely single transiting systems. They're a bit more inclined.
Yes.
So you can see that the compact systems tend to suffer more giant impacts.
Yes. Yes, they do. Got a little outlier out here too. All right.
Hmm.
Okay. All right. I'm with you. Good. Okay, so there's that. Slow down. Let's talk about photo evaporation.
Yeah, so use the atmospheric escape model from B Planet, from Barnes et al. I highly recommend. They have great documentation. It's all
Yay.
open source.
Oh, yay. That gets a thumbs up.
Um, and so I think another key assumption of this whole model is that we're just using one star and one star's X-ray and ultraviolet flux history. Clearly all stars don't have the same X-ray and ultraviolet history.
Surely.
And so there's a lot less scatters we'll see in which planets get photoevaporated.
Okay.
Like the radius gap isn't completely empty, as you might assume if photoevaporation was the dominant process. And
Yeah.
at least some of that is due to the fact that not every star puts out the same amount of UV over its history.
Yes. 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 Definitely. Okay.
So next we assign detection probabilities.
Yeah.
Basically trying to use the same sort of thing as the Kepler pipeline. Same signal to noise ratio.
Okay.
Um,
CP. Okay. And delta here is the transit depth. Must be. Yes. Here we go.
yes.
Okay.
And so because our giant impact planets are generally a little bit larger, because I think more of them will keep their atmospheres, and the planets that we do detect, we detect slightly more
You can be a
of
little
the
high.
giant impact planets.
Yeah. Yeah. You'll be a little high. That's okay. Cool. I'm with you. Let me get into. What do you want to do? You want to get into some of the results table?
Oh, we can go to the results first and maybe come back to this table.
Okay. All right. Okay, let's do an image. There we go.
So it turns out that 85% of planets or so have the same outcome underneath giant impacts and photoevaporation, in that either they both the sets of planets keep their atmosphere or they both lose them.
Okay.
But what we're really interested in is the differences. And so you can see the yellow and purple points on this plot are planets where there is a difference. So
Yes.
yellow is you have gone down in density from giant impacts to photoevaporation, meaning that in giant impacts they've lost their atmosphere. These have a giant impact, but under photoevaporation these would not have lost their atmospheres. And purple is the opposite, where in giant impacts they have not lost their atmospheres, where in photoevaporation they have. And I guess this is sort of the key discovery.
Nice. One question: What is rho? The density of what?
The density of the planets.
Number density. Mass density.
No, so yeah, mass density is in
Mass density.
grams per
Oh,
centimeter cubed.
I'm with you. I'm good.
Yeah.
Thank you.
So we also have plotted on here in gray some of the known kind of super puff planets, because what we find here is that in giant impacts you can have these super puff planets because they don't get photo evaporated.
Okay.
And so they can exist close to their host star. Whereas under photo evaporation, well, anything interior to some semi-major axis will be getting photo evaporated.
Yes.
And so that's a population of planets that doesn't exist under a dominant photo evaporation paradigm. And similarly for the yellow planets, those planets are a lot denser
Yes.
than this sort of standard like terrestrial planet. And
Okay.
it's because these planets would not would have been able to hold on to their hydrogen helium atmosphere under photoevaporation. But if they suffer a giant impact, well, all of that gets liberated and you're left with this extra dense core.
Yes. Okay. Nice. All right.
And I guess for photoevaporation, there also exists a kind of far away sort of, yeah, that little cluster there.
Yeah, this close to clump here, right?
But for the most part we don't actually detect those. So this is a plot of all of the planets that exist in the simulations.
Cool.
But if they're outside of 1AU, we have a hard time detecting them.
Yes. Okay. Very good. Okay, so that's the difference. This is a nice plot. All right. Very cool. Okay. Oh, and on the super puffs, they have error bars?
Yeah, so those actually, so since we don't actually, since the other planets are simulated, I know their radii and their densities exactly, but for the superbuffs in general,
Ah,
they have kind of big error bars, although I think that has changed in the last few years. So
okay. I'm with you. Okay, thank you. Very good. All right, let's move down to period.
so this is the plot of a full population of things with giant impacts on the left and photoevaporation on the right.
Okay.
And you can see the radius gap in the photoevaporation plot, and that there
Mhm.
is basically nothing in the middle.
So there, but yes.
And I guess you can see elements of this plot in all of the other plot, but I kind of want to draw attention to the fact that
Interesting.
for a lot of the large planets, so the upper group of planets in both of these plots, you
Yes.
end up missing a lot of the large planets in photoevaporation, which is what we just talked about. Those
Mhm.
planets aren't allowed to exist at those periods.
Yes. Okay. You get histograms.
So yeah, so for
Evaporation on the right.
mhm. Yeah, so for photoevaporation, if we were to have different UV histories for the star, then you would see some filling in there. But I think this makes the point that the gap should be broadly empty.
Yes. Yes, even if you allow for relax some of the assumptions made. Yes.
Mhm.
Uh-huh. Uh-huh. Well, it seems like on the erosion here, I mean, we're definitely populating. The gap is smaller. Let's put it that way. It's not
Mhm.
as pronounced as photoevaporation. Mm-hmm. Cool. Okay. Good. I'm with you. Let's go down. Radius distribution. ED10, ED4. Here we go.
So I guess we just talked about this. This is the
Yeah.
movement of different planet populations from
Mm.
giant impacts to photoevaporation. I think it's particularly powerful because we're using the same set of planets under different assumptions.
Yes. Uh-huh.
And so being able to see where they move like really tells us something about what's going on.
Yes. And how they relate to each other and how they can go back and forth. Nice. Okay. I'm with you. Good. Okay. And now we got hot, cold, radii.
Yeah, so these are the intrinsic radii distributions of these two populations of planets. Um, you can see that giant impact planets are a little bit larger in general than photoevaporation planets, especially for the compact, cold,
Cold ones.
multi-transiting systems.
Yeah. Yeah.
Um,
Okay.
but if you scroll down, you'll see how this changes with the observed. So once we run our observation or Kepler survey, um, you can see that this changes a little bit. You lose out on a lot of the smaller planets and
Yeah. Okay.
really can only start detecting planets past about 1 Earth radii.
Yeah.
But
Okay.
you also lose out on a lot of the larger planets because those planets are further out in
Further, even
general.
further out, right? Okay.
And so the observed sample is basically drawn from a mixture of the hot and cold systems. We think that the mixture runs about 90-10 for um, hot versus cold, although
Yeah.
cold planets in multi-transiting systems make up a lot of the planets that we actually see. That's because they're multi-transiting.
Yes. Yes. Okay. Uh-huh. Okay. Definitely a gap. Definitely a gap. Okay. Good. I'm with you.
Right.
Figure 6.
Yeah. So the next figure is a
Radius gap.
comparison directly of photoevaporation versus giant impacts.
Very good. Okay.
And so this histogram really shows there should be basically nothing around 2 Earth radii.
Mm-hmm.
Um,
All
under photoevaporation.
Uh-huh.
But you get something
Mm-hmm.
with giant impacts, and I think even a bigger signature than just like something in the gap is kind of the slopes of the gap here. Things
Okay.
drop off a cliff for photoevaporation once you get to
Yeah.
about 1.5
Yes.
Earth radii, because that's
Here
about
it's
how big those planets could be. They're rocky,
yes.
but you get a little smearing and
Mm,
radius space because you can get all sorts of densities.
true. Okay.
So if you combine the two, you end up getting something that does look sort of similar to the current radius gap. Because you can tune the knob on how much of this is photoevaporation and how much of this is giant impacts. So this
Mm-hmm.
plot is just 50-50.
Yeah. Mm-hmm. Mm-hmm. You can modulate between these two. Okay.
So yeah, I guess we broke this paper up into what
Okay.
are some things that you could look for to tell you what's going on as far as whether it's photoevaporation or giant impacts, and this is one of them.
Okay.
The exact amount of filling in the gap.
Yes. Yes. Okay.
Because with reasonable assumptions for like what UV history of stars is, and how planets are made, you can come up with a number for how filled the gap should be.
Yes. Mm-hmm. Mm-hmm. Very nice. I'm with you. Okay. Figure 7. There's a radii. Ooh, multiplicity. Right. Right.
Yes, so this is another thing that we
Right.
found that is a signal. It seems like that for photoevaporation, so that's the bottom panel here, the probability that an observed planet has an atmosphere um, doesn't change very much with multiplicity. It's between about 20 and 40%. But for giant impacts,
Yeah.
when you have a triply transiting system, so or more,
Yikes.
the probability that those planets have retained their atmosphere shoots up to over 80%.
Indeed. Well separated. Wow. Okay.
So this would be a key signature to look for. Like when you look at multi-transiting systems, are they more likely to be gaseous than single transiting systems?
Yeah. And what is it that about triples that drives such a large delta
Mm.
between the two
So
scenarios?
so when you're looking at a triple or more system, you're
Mm-hmm.
probably looking at most of the planets in the inner part of the system.
Fair.
And for photoevaporation, if they're in the inner part of the system, then they've most likely lost their atmospheres. But giant impacts is basically stochastic.
Okay.
There's like a small
Why not?
semi-major axis dependence on like the frequency of impacts, but
Okay.
it's basically random which out
Okay.
of say a group of 4 planets that are orbiting within 30 days
Okay.
gets their atmosphere stripped.
I got it. Got it. Very good. Okay.
And so the probability goes way up because sometimes you'll have 2 of them that don't get hit, you'll have 3 of them that don't get hit.
Right. Okay. Cool. Thank you. I'm with you. Got it. Mm-hmm. Very nice. Okay. And here's our fifth equation. The monoticity statistic, density.
Yeah, so there's a paper by Gilbert and Fabricki back in 2020 which detailed a lot of different ways to quantify things that we know about planetary systems. One of them was monotonicity, like how size ordered are the planets.
Yes.
In general, you expect the planets to have some slight size ordering. There's this whole peas in a pod discussion that's been going on. So planets are generally about the same size, but if there is a size ordering, it will be smallest to largest.
Okay.
Um,
Mm-hmm.
that's what you expect, especially under photoevaporation, where the inner planets get photoevaporated, the outer ones don't.
Okay. Sort of the funny cue here was mass distribution.
Mhm.
Okay. Or yeah, okay, that makes sense. Or PS. Okay, good.
And so if you plot this for photoevaporation planets versus giant impact planets, the
Mhm.
giant impact planets are very slightly less monotonic, like they're less likely to
Yeah.
only grow in radius,
Okay.
which, as we've just discussed, is because, well, any of those planets can have their atmosphere removed, and
Yes.
any of them could keep their atmosphere. And so that basically randomizes
Yes.
the size ordering that planets come out of planet formation with.
Yes. Okay. Uh-huh. Uh-huh. Oh, and just to orientate, a monotonicity of 0 would mean what?
That would mean everything is the same size.
Yes. Okay.
And so positive would be is going up in size, and
Yes.
negative would be going down in size.
I'm with you. Very good. Okay. Okay. Good. And then we have my favorite plot in the whole article. Design-wise, I think it's lovely.
Thank you. I put a lot of work into this.
Yeah, I love the design on this one. It's very nice. Mm-hmm.
Um, and so our final thing that we suggest as a way to figure out what's happening is
Okay.
you can look at, if you get good enough constraints on the density for planets. So a a characteristic error of like 1 gram per centimeter cubed or 2 grams per centimeter cube. You can look at the clustering of
Woo.
these plots of these planets in density space,
Mm-hmm.
and the degree of clustering will tell you what effect is dominant.
Mm-hmm. Okay.
So for giant impacts, the clustering is much stronger. So you get stronger clusters at low density and high density than you do for photoevaporation for the same number of planets.
Okay. Yes. I'm with you. And the gray curves are.
So this is a Gaussian mixture model. So
Got it.
you're modeling this distribution as a combination of two Gaussians, so
Yes.
two characteristic densities and then some spread from that.
Yes.
Um,
Okay.
and the gray curves are basically like the different iterations of this weight between the two.
Okay. Okay. Good. And coloring the F is the flux.
Yes. So that's trying to show like insulation of these planets.
Yeah. Okay. Okay.
So I guess this is something that people have been hard at work on for the last couple of years since this
Yeah.
project started. Getting high resolution RV observations of lots of small planets, especially from tests. And so I think this is something that could probably be reasonably done soon.
Mm-hmm. Mm-hmm. Lovely. Very good. We got a few predictions in there too. Awesome. Very good. Okay, and then we come into our conclusions. So what do you want to say as the punchlines?
Yeah. So so there are these diagnostic tools for determining which atmospheric loss mechanism is dominant.
Mm-hmm.
The emptiness of the radius gap, as we talked about, it should be close to completely empty when planets are only subject to photoevaporation, but
Yes.
not empty when giant impacts are dominant. Um, in fact, we see that there are some systems where you have a planet interior to one that has been photoevaporated, or
Okay.
you have a planet that's interior to one that is not photoevaporated, and the exterior one appears like maybe it is. So
Uh-huh.
something where it's going on.
Uh-huh.
Then number two, the occurrence of atmospheres as a function of transit multiplicity. You should see a huge jump in the number of fluffy planets
Yes.
um, when you go to triple plus systems.
Mm-hmm.
If giant impact is the dominant mechanism.
Yes.
Um,
You saw that. Yes.
Now, I don't exactly expect giant impacts to be the dominant mechanism, but considering the size of the difference, if giant impacts does play at least like a sizable role, you
Yeah.
expect to see some difference. Um, Number 3, the size ordering of planets as orbital period increases, so the monotonicity. Giant impacts will scramble the size ordering.
Yes.
This one I think will be a little bit tough, but as we get more and more planets, it'll become easier. And then the existence of high density cores and the low density like super puff planets happens when giant impacts are dominant.
Okay.
And so I think that will take a lot of work, especially for the other methods of atmospheric loss, to see like, can you have these planets result from those also?
Yeah. Okay. Very cool. Very nice. Awesome paper. Quadry, I want to thank you so much for walking us through your very awesome APJ article. Thanks.
Yeah, no problem.
And you mentioned it a couple of times, or you hinted at it a couple of times. So let me go ahead and push on it a little bit. And where do you think we go, let's say, over the next 2 to 5 years on this topic? Is there going to be, for example, could there be additional in-body simulations? Could there be relaxing of the assumption of a solar? So you get the solar UV, but there's variations in that. Is there additional, maybe some new observation coming, maybe from Planck or one of the other missions along those lines? And just sort of next steps. So where do you think we go with this topic over the next couple of years?
Okay, well, I'm personally doing a project on this topic, which will hopefully be out in the next couple months. Looking at when you have planets that are in the radius gap, what do their neighbors look like? And the answer may surprise you.
I look forward to it.
But
leading hint.
I think there's a lot of room to improve on like our method here, like it's basically relaxing some of the assumptions. But as you do that, the problem increases substantially in complexity, and I'm not sure that
fair enough
we'll get a better answer, like enough of a better answer to warrant increase in complexity. I think most of the work that has to be done in this space is observational. So yeah, people are hard at work getting accurate planet radii, accurate planet masses, and that's the actual information we need to be able to answer this question.
Yeah. Observation rules. Yeah. That's one theorist to another.
Yeah, we can simulate all day.
Yeah, all we want. But at the end of the day, you got to, what is the ground truth reality? So yeah, very cool. Very cool.
I think there seems to be some bias in a lot of the small planet measurements because they're measured through TTBs, and those planets appear to be lighter than the RV planets. And so figuring out exactly what's going on there, I think, will be key in actually, first of all, knowing what the mass and radius planets actually are, and like seeing how that is entangled with their formation.
Yes. Very cool. Very nice. Well, I really look forward to seeing this topic advance over the next couple of years, and I really look forward to seeing Dr. Chance as we get there. So very cool.
All right, thank you.
And that will do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.